Imagine waking up to the headline, NASA telescope finds a planet with a 99.7% chance of life. It sounds like the biggest story in human history, proof that we're not alone. But what's actually behind that number is more complicated, and honestly, more interesting than the headline itself. In early 2025, scientists using the James Webb Space Telescope turned their attention to a planet called K2-18b, about 124 light-years away, in the constellation Leo. They weren't expecting a media frenzy. They were just collecting spectra, the light signatures that reveal what a planet's atmosphere is made of. But when they analysed that light, they found something almost no one expected. Traces of a molecule called dimethyl sulfide, or DMS, a gas that, on Earth, is produced only by living organisms like ocean plankton. The data looks solid enough that they gave it a 99.7% confidence level. That's what led to the viral claim, a 99.7% chance of life. It's not quite that simple, but what it does mean is that for the first time, we may have detected a chemical fingerprint in another planet's atmosphere that looks eerily like biology. If that holds up, it could be the first real sign of life beyond Earth. When the story broke, it felt like the moment everyone had been waiting for. News outlets splashed the same line across their headlines. James Webb finds a planet with a 99.7% chance of life. On social media, people posted excited threads about alien oceans, microbial civilizations, and the idea that humanity had finally found its cosmic neighbour. Even science communicators and astrophysicists, people who usually tread carefully, had to admit, this sounded huge. But within the excitement, something got lost. What scientists had actually said wasn't, we found life, but we found a gas that, on Earth, is only made by life. Those two statements might sound similar, but they're galaxies apart. The planet in question, K2-18b, has been known for a while. It was first discovered in 2015 by NASA's Kepler mission, which spent years looking for tiny dips in starlight, clues that a planet had crossed in front of its host star. When K2-18b was first catalogued, it was just another entry among thousands of exoplanets. It didn't seem remarkable at the time. What caught scientists' attention later was where it sat, right in the habitable zone of a small red dwarf star about 124 light-years away in the constellation Leo. That means, at least theoretically, the planet could have temperatures suitable for liquid water, a basic ingredient for life as we know it. For years, that was enough to keep K2-18b on the maybe list. It wasn't Earth-like, far from it. But it was interesting. Then the James Webb Space Telescope, JWST, came online, armed with the most sensitive infrared instruments ever sent to space. Webb's job wasn't just to look at pretty galaxies or early universe stars. One of its most exciting roles was to study exoplanet atmospheres. By analysing starlight that filters through a planet's air as it passes in front of its star, JWST can detect faint chemical fingerprints, tiny shifts in light that reveal which molecules are present. When astronomers pointed JWST at K2-18b, they expected to see water vapour and maybe carbon-based gases like methane or carbon dioxide. What they didn't expect was a faint but distinct signal for dimethyl sulfide, DMS, and dimethyl disulfide, DMDS. On Earth, both of these compounds are produced exclusively by biological activity, mostly by marine plankton and bacteria. There's no known geological or chemical process here that makes them in significant amounts. So when Webb's instruments picked up that signal, the research team had to check and recheck their work. After a long statistical analysis, they reported a 99.7% confidence level that the signal was real. To scientists, that's strong but not definitive. What's called a 3 sigma detection. It means that based on the data, there's only a 0.3% chance the result is due to random noise, but that number got twisted in headlines and social media posts into something it wasn't. A 99.7% confidence in the detection of a molecule is not the same as a 99.7% chance of alien life. The researchers themselves made that clear in their publication and press statements, emphasizing that while the result is the strongest evidence yet of a potential biosignature beyond Earth, it's not proof of life. Still, that nuance didn't stop the public imagination from running wild. For decades, we've been conditioned to expect one big moment, the day humanity finally confirms life elsewhere. Every time a discovery gets close, from Mars methane to Venus phosphine, the excitement spikes and then fades as results are revised or disproven. But this time felt different. JWST is not a single instrument experiment or an ambiguous sensor reading. It's a billion-dollar observatory, purpose-built to do exactly this kind of analysis. Its instruments don't just look for one molecule, they cross-check many, allowing scientists to build a detailed picture of a planet's atmosphere. So when DMS showed up in K2-18b's data, it carried more weight than previous false alarms. Even the cautious wording from NASA, phrases like potential biosignature candidate, didn't dampen the fascination. People weren't celebrating because life was proven. They were celebrating because, for the first time, the technology to truly find life might actually work. And that's the real reason the story went viral. It wasn't just about aliens, it was about progress. For decades, our search for life has been a waiting game, limited by instruments that couldn't quite reach far enough or see clearly enough. The James Webb Space Telescope changed that overnight. It gave humanity its first realistic shot at detecting life indirectly, through the chemistry of another world. But this new power also brings new challenges. The telescope's sensitivity means scientists must interpret every detection carefully. A faint blip that looks like biology could easily be caused by an unknown chemical process we don't yet understand. The same molecule could mean different things in different environments. On Earth, DMS comes from life. On another planet, it might not. That's why the team behind the discovery has been careful to say possible biosignature, not confirmed life. Still, even with all those caveats, the excitement is justified. K2-18b may not be our first alien world with confirmed life, but it represents something just as important. The first time we've seen a credible candidate. The 99.7% number, once you look past the clickbait, is really a measure of confidence that we've detected something extraordinary in that planet's atmosphere. What it means is that, at long last, we're close enough to start asking the right questions with the right tools. The headline may have oversimplified things, but it captured a genuine truth. The search for life beyond Earth is no longer a distant dream or a vague hope. It's happening right now, with data coming in light year by light year. And the world that made everyone stop scrolling, K2-18b, is the first one that's giving us a glimpse of what could lie beyond the boundaries of our own blue planet. K2-18b sits in a quiet corner of the galaxy, orbiting a small, cool, red dwarf star, about 124 light-years away in the constellation Leo. To picture that distance, imagine travelling at the speed of the fastest spacecraft humans have ever built. Voyager 1, moving at nearly 17 kilometers per second. At that speed, it would still take more than 2 million years to reach K2-18b. In other words, we're never visiting this planet in person anytime soon. Everything we know about it comes from the faint starlight that passes through its atmosphere on its way to us. The star it orbits is known as K2-18, a small M-type dwarf that's cooler and much dimmer than our Sun. Because it gives off less light, its habitable zone, the region where temperatures could allow liquid water, sits much closer to the star. K2-18b orbits right in that zone, completing a full orbit every 33 days. That's incredibly fast compared to Earth's 365-day year. But because the star is so faint, that short orbital period doesn't necessarily mean the planet is overheated. In fact, calculations suggest that the temperature at the top of its atmosphere could be similar to Earth's average temperature. Maybe even cool enough for clouds and possibly oceans. K2-18b itself is a sub-Neptune, roughly 2.6 times Earth's radius and about 8.6 times as massive. That combination makes it too big to be a rocky world like Earth, but too small to be a gas giant like Neptune. Instead, it's part of a class of planets that scientists didn't even know existed until the past decade, something between the two, with a thick atmosphere of hydrogen and helium wrapped around a potentially water-rich interior. Planets like this are often called Hycean worlds, a blend of hydrogen and ocean. And they're starting to look like some of the most promising places to look for life. Because K2-18b is so close to its star, it probably shows the same face to it all the time, a phenomenon called tidal locking, similar to how the moon always shows the same side to Earth. One hemisphere bakes in perpetual daylight, while the other lies in permanent darkness. The temperature contrast between those sides could create fierce winds and global weather patterns, unlike anything we experience here. But if there's a thick enough atmosphere, or even a global ocean, that could redistribute heat and make parts of the planet surprisingly mild, the planet's density suggests that beneath that light, hydrogen-rich atmosphere, there may be a deep layer of high-pressure water, liquid closer to the surface, then turning into exotic, supercritical water deeper down, where it behaves like both a gas and a liquid. Below that might lie an icy or rocky core. Scientists have run hundreds of computer models to test different combinations of atmospheric thickness, temperature, and composition that could match Webb's observations. Many of those models agree on one key point. Conditions there could, in principle, support chemistry similar to what we consider necessary for life. Now, even if K2-18b has oceans, they wouldn't be like ours. Because of the high pressure from its thick atmosphere, the sea might be hundreds of kilometers deep, sealed under a layer of hot, dense vapor. The air above it would be mostly hydrogen instead of nitrogen and oxygen, and the light from its red dwarf star would give everything a deep crimson hue. It's not the kind of world you'd step onto. You'd need to float in its upper atmosphere or swim through water far denser than anything we know. But in those conditions, simple, microbial life, if it ever arose, could still exist, perhaps feeding on chemical energy rather than sunlight. That's what makes K2-18b fascinating. It's not an Earth twin. It's not a second home for humans. It's something stranger, a hybrid world that challenges what we thought habitable meant. For decades, scientists focused on finding rocky planets like ours, assuming that only Earth-like conditions could host life. But the discovery of K2-18b's atmosphere forced them to widen that search. If life can exist in the dense, pressurized air of a hydrogen world, the number of possible living planets in our galaxy could be vastly higher than anyone imagined. And there's another reason this planet stands out. Around small red dwarf stars like K2-18, radiation bursts and stellar flares are common, often stripping atmospheres from nearby planets. Yet K2-18b seems to have held onto its thick gaseous envelope for billions of years. That stability means the planet's environment could have remained relatively steady over long timescales, long enough for complex chemistry, or even life to develop if it ever began. Every measurement of this planet reminds scientists of one key fact. Our idea of a habitable world is evolving fast. K2-18b shows that planets don't have to be Earth clones to be worth investigating. In some ways, its unusual size and atmosphere make it even better for remote study. A big, puffy planet blocks more starlight and leaves a clearer spectral signature, which is exactly what allowed the James Webb Space Telescope to detect those faint chemical fingerprints in the first place. So when you hear about that planet with a 99.7% chance of life, it's not just about a number, it's about a place so far away that we'll never visit it, but one that's already changing how we think about life itself. It orbits a dim red star, bathed in perpetual twilight, wrapped in hydrogen and water vapor, and yet somehow, it's now one of the most important planets in the known universe. When scientists first looked at K2-18b's measurements, it didn't fit neatly into any familiar category. Its mass and radius put it between two very different kinds of planets, rocky worlds like Earth and gas giants like Neptune. That middle ground, what astronomers call a sub-Neptune, was once a mystery. We didn't have anything like it in our own solar system, so no one knew whether these worlds were puffy mini Neptunes covered in thick gas, or scaled-up Earths with vast oceans. Over time, computer models started to fill in the picture. K2-18b, based on its density, couldn't be solid rock. It was too light for its size. That suggested a thick, extended atmosphere, mostly hydrogen and helium, maybe hundreds of kilometers deep. Beneath that atmosphere could be a global ocean or layers of exotic water under high pressure. These characteristics inspired the term Hycean world, short for hydrogen plus ocean. The name describes a planet that's neither rocky nor purely gaseous, but something in between, a watery world wrapped in hydrogen. A Hycean planet doesn't need to be Earth-like to be habitable. In fact, it could be more forgiving. The hydrogen layer acts like a thermal blanket, trapping heat and keeping temperatures stable across the planet's surface. That means even if one side is permanently facing its star, like K218b likely is, heat could circulate through winds and ocean currents, creating mild temperate regions where chemistry can thrive. This type of environment changes how we think about life. For decades, astrobiologists assumed the best places to look were rocky planets with thin atmospheres, mild climates, and surface oceans. That was the Earth-like model. But K218b suggests that life might also survive in deep oceans, under thick gas layers, feeding on chemical gradients instead of sunlight. On Earth, microbes do exactly that, thriving near hydrothermal vents, miles below the ocean surface where no sunlight reaches. The chemistry there runs on hydrogen, methane, and sulfur compounds, the very same types of molecules Webb found in K2-18b's atmosphere. If those molecules on K2-18b are being replenished from below, it might mean something is actively producing them. On Earth, DMS and DMDS, dimethyl sulfide and dimethyl disulfide, are made by plankton and bacteria in the ocean, released into the air as part of the sulfur cycle. They don't last long in the atmosphere, they break down quickly, so detecting them suggests a continuous source. That's why Webb's discovery caused such a stir. It implied that something, possibly life, is keeping those molecules present. To understand how this might work on K2-18b, imagine a world where sunlight filters through a dense, pink-tinged sky. The hydrogen-rich atmosphere glows with a reddish tint from the dim light of a red dwarf sun. Below that sky lies an ocean that could stretch thousands of kilometers deep. Near the surface, it might be liquid water. Deeper down, the pressure would squeeze it into a supercritical state. Neither a liquid nor a gas, but something in between. It's an alien ocean, dense and hot, perhaps infused with methane and ammonia. And yet within that mix, it's possible that simple, organic chemistry, the kind that once kick-started life on Earth, could take hold. Of course, this is speculation. Scientists can't see the ocean directly. They can't even see the planet's surface, if it has one. But the chemistry we detect in its atmosphere is like a message from below, a snapshot of whatever processes are shaping that world. If DMS is really there, it's coming from somewhere. And whatever that somewhere is, it's interesting enough to warrant deeper investigation. Another fascinating thing about K2-18b is that it's large enough to retain a thick atmosphere for billions of years. That stability is crucial. Life, at least as we know it, needs time. Long, uninterrupted spans of chemical evolution. A planet that's constantly bombarded by radiation or losing its air wouldn't give biology much of a chance to establish itself. K2-18b seems to have avoided that fate. Its red dwarf star is relatively quiet compared to many others, and the planet's magnetic field might help shield its atmosphere from solar wind. Even so, it's not paradise. The surface pressure could be hundreds of times greater than Earth's, and the lower atmosphere may be hot enough to crush or vaporize most materials. Any life that exists there would need to adapt to conditions we'd find extreme. But life on Earth has already proven it can thrive in places once thought impossible. Boiling vents, acidic lakes, subglacial oceans. That's what gives scientists hope that K2-18b's environment, strange as it seems, might not be sterile. What makes the Haitian model so exciting is how it multiplies our odds. For years, the search for life focused on finding rocky planets exactly like Earth. The same temperature, the same air, the same sunlight. But the more we learn, the more we realise life might not be so picky. If hydrogen-rich ocean worlds can support biology, the number of potentially habitable planets in our galaxy jumps dramatically. Red dwarfs like K2-18 are the most common type of star in the Milky Way, and many are known to host planets of similar size and composition. In other words, if K2-18b turns out to be alive, it probably won't be alone. Even if future data shows that DMS on K2-18b isn't biological, this discovery still marks a turning point. It proves we can study the atmospheres of distant worlds in enough detail to find subtle, life-related molecules. We're no longer limited to guessing based on distance or size. We can now probe their chemistry directly. That's something scientists have dreamed of since the first exoplanet was discovered in 1995. So while K2-18b might not be a second Earth, it could be something even more profound, a new category of habitable world. It challenges our assumptions, stretches our definitions, and forces us to ask a bigger question. Not, can life exist in Earth-like conditions? But, can life exist anywhere chemistry allows it? If the answer is yes, then K2-18b isn't just an interesting planet. It's a doorway to understanding how common life might really be in the universe. And that, more than any single number or statistic, is what makes this discovery worth paying attention to. By the time the James Webb Space Telescope began its scientific operations in mid-2022, astronomers already had a short list of exoplanets they wanted to observe first. These were worlds that looked particularly promising, not because they were Earth-like, but because previous telescopes had already hinted at something unusual in their atmospheres. Near the top of that list was K2-18b. Back in 2019, the Hubble Space Telescope had taken a closer look at K2-18b during its transits, the moments when the planet passes in front of its star as seen from Earth. By examining the way starlight filtered through the planet's atmosphere, Hubble detected water vapour, the first time water had ever been seen in the atmosphere of a potentially habitable zone, exoplanet. That discovery immediately made K2-18b stand out. Water vapour meant the planet's air wasn't just a blanket of gas, it was part of an active chemical system. For scientists, that's a major clue that something interesting could be happening beneath it. But Hubble's instruments, designed in the 1990s, had limits. It could detect broad features in an atmosphere's composition, but it couldn't pinpoint faint or complex molecules with much accuracy. Its infrared detectors were less sensitive than Webb's, and its range of observation stopped short of the wavelengths where many organic and volatile molecules reveal themselves. That's where JWST comes in. Webb was designed to fill exactly that gap, to see in deep infrared with enough resolution to separate overlapping chemical fingerprints. When Webb began its first exoplanet campaign, scientists specifically wanted to answer the question Hubble had raised. If there's water vapour on K2-18b, what else is in its atmosphere? Are there gases like methane or carbon dioxide, molecules that on Earth come from biological or geological activity? And if those gases appear in certain ratios, could that hint at processes similar to those that sustain life here? The Near-Infrared Imager and Slitless Spectrograph, NIRISS, and Near-Infrared Spectrograph, NIRSPAC, onboard Webb became the tools for this task. Together, they can detect light signatures that are 1 billion times fainter than the star itself. Webb observes K2-18b during multiple transits, gathering data from the tiny fraction of starlight that passes through its atmosphere. Each molecule absorbs specific wavelengths of light, creating a unique pattern, like a barcode. By matching that pattern to known molecular data, astronomers can tell what gases are present and in what amounts. This method, called transit spectroscopy, is the foundation of modern exoplanet science. It's a remarkably indirect approach. No one ever sees the planet itself, just the way its atmosphere interacts with light. But with enough precision, that light carries a wealth of information. For instance, methane absorbs light near 3.3 microns, carbon dioxide near 4.3 microns, and water vapour at several bands across the near-infrared. Webb's instruments are sensitive across all those ranges, meaning it can capture a complete chemical snapshot of a planet's atmosphere in a single observation. So when the Webb team revisited K2-18b, they weren't starting from scratch. They were following up on a known clue. The goal was to test whether this planet could fit into a new category of potentially habitable worlds. Scientists suspected it might not be rocky, but it could still host liquid water in the right conditions. That was enough reason to take a deeper look. But there was another, more practical reason for choosing K2-18b. Many exoplanets in habitable zones orbit dim, cool red dwarf stars, which are ideal for transit studies. Because those stars are small, even a modestly sized planet blocks a noticeable fraction of their light when it passes in front. K2-18b, with its relatively large size and short orbital period, produces a strong, clear signal that Webb can easily detect. That makes it a perfect laboratory for testing the telescope's capabilities. Webb's first set of observations revealed that K2-18b's atmosphere contains methane, CH4, and carbon dioxide, CO2, in ratios that suggest a hydrogen-rich, possibly ocean-bearing world. But then came the surprise. Within those same spectral bands, the data hinted at faint but consistent features corresponding to dimethyl sulfide DMS, a molecule no one expected to see on an exoplanet. The DMS signature was subtle, right at the edge of detectability. That's why the research team used multiple independent analysis pipelines, different methods of processing and interpreting the raw data to confirm the signal wasn't an artifact. Every test they ran returned roughly the same result: a weak but statistically significant sign of DMS at a 99.7% confidence level. For perspective, that's the same threshold particle physicists use to call something a strong indication of a real effect. It's not enough for a discovery claim. That usually requires a 5 sigma, 99.9999% level, but it's much stronger than noise. To make it even more compelling, the same dataset also hinted at dimethyl disulfide, DMDS, a chemical cousin of DMS that sometimes appears when DMS breaks down under ultraviolet light. At this point, astronomers had two options: treat the signal as a potential false positive and move on, or take it seriously and plan more observations. They chose the latter. The reason was simple: DMS is rare. On Earth, it's almost exclusively produced by marine microorganisms as part of their metabolism. No known abiotic process produces DMS in detectable quantities under normal planetary conditions. If a similar process were happening on K2-18b, it would be one of the most exciting findings in decades. That's how a relatively obscure planet discovered by Kepler suddenly became one of the most studied objects outside our solar system. Webb's early results didn't just support the idea that K2-18b might have water, they hinted that something in its atmosphere could be actively replenishing complex organic molecules. But as scientists celebrated the detection, they also urged caution. Detecting DMS is not the same as proving life exists. It's entirely possible that some unknown chemical pathway could create DMS in a hydrogen-dominated atmosphere without biology. The challenge is that no one's found a plausible one yet. To figure that out, astronomers will need more data, more transits, more wavelengths, and more time. For now, K2-18b has become a kind of natural experiment, a test case for how we'll handle potential biosignatures in the coming years. It's the first world where a major telescope has detected a molecule so strongly associated with life. It's also a reminder that the biggest discoveries often come from revisiting things we already thought we understood, with better tools and sharper eyes. So while the public saw a sensational headline about 99.7% chance of life, astronomers saw something even more meaningful: proof that their instruments are now precise enough to detect the faint chemical echoes of biology across light years of space. Whether or not K2-18b turns out to host life, it's already accomplished something extraordinary. It showed that our search can finally move from speculation to observation. If there's one thing that separates the James Webb Space Telescope from every observatory before it, it's what it can see in invisible light. Unlike Hubble, which mostly observes invisible and near-infrared wavelengths, Webb was designed to look deep into the infrared spectrum, the realm where heat and molecules leave their fingerprints. That's where the clues to life hide. When astronomers study an exoplanet, they can't take a direct image of it. These planets are far too small and too faint, completely lost in the glare of their parent stars. But when one of them passes directly in front of its star, a transit, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. The atmosphere acts like a thin lens, absorbing and scattering specific wavelengths, depending on what gases it contains. That's the magic Webb is built for. Its instruments, primarily NIR-SPAC, near-infrared spectrograph, and NIRISS, near-infrared imager, and slitless spectrograph, break that light into thousands of tiny, wavelength slices. Each molecule, water, methane, carbon dioxide, oxygen, or even complex organics, absorbs light at unique frequencies, leaving dark lines in the spectrum. These are known as absorption features, and together they form a molecular fingerprint. To give a sense of scale, the difference between a star's light during a transit and when the planet isn't transiting is often less than 1 part in 10,000. Webb measures those tiny variations repeatedly, building up an extremely precise spectrum. For each planet, scientists then run computer models, simulating how different mixtures of gases would affect the starlight. The model that best fits the observed spectrum tells them what the atmosphere is likely made of. For K2-18b, this process involved analysing several wavelengths where key gases absorb infrared light. Water vapour shows up near 1.4 microns, methane near 3.3 microns, and carbon dioxide around 4.3 microns. DMS and DMDS leave subtler imprints, but they show characteristic absorption features in overlapping ranges around 3 and 7 microns. When Webb's data matched those features, it wasn't a random coincidence. It was a clear signal that something resembling DMS was present in measurable quantities. To make sure, the team performed multiple checks. First, they compared the data from two different instruments, NIRISS and NIRSPEC, to confirm the same pattern appeared in both. Then they used independent data processing pipelines, essentially different mathematical approaches to cleaning and interpreting the spectra, to rule out systematic errors. Even after accounting for instrument noise and calibration uncertainties, the DMS signature remained. That's what led to the quoted 99.7% confidence level, a 3 sigma detection, meaning there's only a 0.3% chance that the signal is due to random noise. Now, that doesn't mean Webb saw alien microbes. What it means is that Webb's sensors picked up a set of infrared fingerprints that are best explained by the presence of DMS-like molecules. Whether those molecules come from biology or chemistry is the next question, and that's where the real detective work begins. One of the key challenges with this method is that spectral overlap can easily confuse things. Different molecules sometimes absorb light at the same or similar wavelengths. For example, methane and ammonia have overlapping bands near 3 microns, which can blur each other's signatures. So distinguishing between them requires both a broad wavelength coverage and very high resolution, two areas where Webb excels. By scanning across a wide range of wavelengths simultaneously, Webb can separate blended features that would have been impossible to resolve with older telescopes. Another challenge is that the light passing through the atmosphere isn't uniform. Some of it comes from higher, cooler layers, some from deeper, warmer regions. That means the resulting spectrum is a composite, shaped by temperature, pressure, and cloud cover. If the planet has hazes or aerosols, tiny suspended particles, they can mute or distort certain features. Webb compensates for this by observing multiple transits under slightly different conditions, letting scientists isolate which patterns stay consistent. In the case of K2-18b, the DMS and DMDS features appeared alongside clear evidence of methane and carbon dioxide. That combination is interesting because, on Earth, these gases coexist in trace amounts due to biological cycling. Methane is produced by microbes and destroyed by oxygen and ultraviolet light. DMS comes from marine organisms. In a purely chemical, non-living atmosphere, these molecules don't usually appear together in stable proportions for long. So while the detection alone doesn't prove biology, the context makes it scientifically intriguing. It's also worth understanding what Webb can't do, at least not yet. The telescope can't map the planet's surface or directly see oceans. It can't measure atmospheric circulation or weather systems in real time. What it can do is provide a snapshot of atmospheric composition averaged across the planet's limb, the thin edge of its disk. Even that limited slice is enough to revolutionize exoplanet science, because it tells us not just what's there, but what might be happening below. To interpret those signals, astronomers use retrieval models, computer programs that simulate thousands of possible atmospheric combinations, and test which best fits the data. These models take into account stellar radiation, chemical reactions, cloud opacity, and temperature profiles. For K2-18b, the best-fitting models all pointed toward a hydrogen-rich atmosphere with water vapour, methane, and carbon dioxide, an environment consistent with a Hycean world. The addition of DMS made the model even more accurate, suggesting it wasn't a spurious signal. One fascinating aspect of Webb's precision is that it can even detect chemical disequilibrium, situations where certain molecules coexist in ways that can't be explained by basic chemistry alone. On Earth, life constantly drives our atmosphere out of equilibrium by replenishing gases that would otherwise disappear, like oxygen or methane. Detecting a similar imbalance on another planet would be one of the strongest indirect signs of biology. That's exactly why the presence of DMS matters so much. it could be part of such a pattern. It's important to remember how extraordinary this capability is. Just a few decades ago, the idea of analysing the atmosphere of a planet around another star was pure science fiction. Even Hubble's detection of water vapour in 2019 was considered groundbreaking. Now, with Webb, we're identifying complex molecules that might hint at life. This is not a technological baby step, it's a leap. To put it simply, Webb acts as a cosmic chemist. It dissects starlight molecule by molecule, turning faint, ancient photons into chemical data. Every transit gives us another piece of the puzzle. What the planet's air is made of, how thick it is, and whether it could support something living. It's an entirely new way of exploring the universe, not by visiting worlds, but by reading them. And that's the power of Webb's design. Instead of looking for little green men or mysterious lights, it searches for chemistry, the universal language of life. That's how we found ourselves here, with a set of spectral lines from a faraway world, suggesting that something, somewhere, is releasing molecules that look suspiciously biological. It's a subtle signal buried in the noise of starlight. But to scientists, it's one of the loudest clues we've ever received. K2-18b is just the beginning. Webb's success in detecting DMS means the same method can now be applied to dozens of other potentially habitable planets. It's a proof of concept, a demonstration that, for the first time, we can use light itself to hunt for life across the galaxy. And as Webb continues to refine its vision, the next detection might not just point to possibility, it might edge us closer to certainty. When the James Webb Space Telescope's first batch of data on K2-18b arrived in early 2025, the research team knew they were sitting on something special. The data didn't just confirm what earlier telescopes had hinted at. It revealed entirely new details that no one had ever seen before in an exoplanet's atmosphere. At first glance, the raw spectrum looked exactly as expected. A broad, bumpy curve with dips at specific wavelengths, where different molecules absorb light. These dips were familiar markers: water vapour, methane and carbon dioxide, all consistent with the idea of a Hycean world, a planet with a hydrogen-rich atmosphere, and possibly an underlying ocean. But when the researchers zoomed in on certain infrared bands, they noticed faint additional features that didn't match any of the known gases modelled in their simulations. The signal was small, almost buried in the noise, but it was consistent. It kept showing up in independent analyses, no matter which processing method they used. This was the first hint of dimethyl sulfide DMS. DMS is a molecule made of carbon, hydrogen, and sulfur, simple elements by cosmic standards, but arranged in a way that, on Earth, is intimately tied to biology. The scientists double-checked the match against every major molecular database. The absorption pattern lined up nearly perfectly. That's when they realised what they were seeing wasn't just another trace gas. It was potentially a biosignature, a chemical produced primarily by living organisms. The more they examined it, the more intriguing it became. DMS is not something that appears spontaneously in large amounts under ordinary planetary conditions. On Earth, nearly all of it comes from marine plankton, tiny organisms that convert sulfur compounds from the ocean into DMS, which then escapes into the atmosphere. Once there, it doesn't last long. Ultraviolet light from the sun breaks it down within days or weeks. That short lifespan means that if you're seeing DMS in an atmosphere, something must be constantly replenishing it. Now here was K2-18b, a world 124 light-years away, showing the same chemical fingerprint in its air. The odds that it was a random coincidence were incredibly low. After months of cross-checking, the team calculated a 3 sigma detection, or roughly 99.7% confidence that the signal was real and not a fluke. In statistical terms, that means if you ran the same experiment 1,000 times, you'd expect to see a false detection only about 3 times. For most fields of science, that's solid evidence. In astronomy, it's tantalizing, but still not definitive. Still, it wasn't just DMS that made the results so compelling. The Webb data also confirmed methane, CH4, and carbon dioxide, CO2, 2 gases that together can signal an atmosphere out of equilibrium. In a simple, lifeless atmosphere, these molecules tend to destroy each other quickly through chemical reactions. To have both present at measurable levels, something has to be replenishing them. either geological activity, like volcanism, or biological processes. Add DMS to that mix, and suddenly the biological explanation starts to look far more plausible. There was also a faint suggestion of dimethyl disulfide, DMDS, a related molecule that forms when DMS reacts with ultraviolet light. On Earth, DMDS is found in trace amounts wherever DMS is present, acting almost like a chemical shadow that confirms its origin. Webb's detection of both strengthened the case that these signals weren't just random noise or data artifacts, they were connected parts of the same chemical system. The researchers didn't jump to conclusions. They ran dozens of tests to see if the DMS feature could be explained by some other molecule, maybe a complex hydrocarbon or an unknown photochemical byproduct of methane, but every alternative failed to reproduce the observed spectral pattern as neatly as DMS did, even when they tweaked the assumed temperature, cloud cover, or pressure of the atmosphere in their models. DMS remained the best fit. One of the most striking aspects of this finding is just how subtle it is. DMS makes up only a tiny fraction of the planet's atmosphere, far less than 1 part per million, according to the models. Yet Webb's sensitivity is so extreme that it can detect that faint signature from across interstellar space. The signal strength was equivalent to catching the scent of a single drop of perfume dispersed in a stadium-sized volume of air. The Discovery team, led by researchers from the University of Cambridge and NASA's Goddard Space Flight Center, presented the findings cautiously. Their paper didn't declare life found. Instead, they called it the strongest evidence yet for a possible biosignature beyond the solar system. They knew how easily such claims could be misinterpreted, especially after the 2020 phosphine on Venus controversy, where initial excitement gave way to skepticism as data was reanalyzed. But this time the data quality was in another league. In the Venus case, the supposed biosignature was right at the edge of the telescope's sensitivity. Webb's readings, in contrast, were clean, repeatable, and backed by multiple instruments. That's why so many scientists described K2-18b as a turning point, rather than just another hint. Even skeptics who doubted the biological interpretation agreed that the observation itself, detecting such faint molecules with such clarity, was groundbreaking. To understand why DMS got everyone's attention, it helps to look at what else Webb didn't find. The data didn't show significant amounts of ammonia, NH3, hydrogen cyanide, HCN, or other gases that might indicate purely chemical reactions in a hydrogen-rich atmosphere. That absence actually makes the DMS detection stand out more. It suggests the molecule isn't a byproduct of random photochemistry, but something specific and sustained. Still, there are non-biological explanations that need to be tested. Some researchers have proposed that DMS could form through high-pressure chemical reactions deep within a planet's atmosphere, especially in environments rich in methane and hydrogen. But these processes haven't been observed or modelled convincingly yet. Until someone can show a realistic non-living mechanism that produces DMS in such quantities, the biological possibility remains on the table. This discovery also changed how astronomers plan future observations. Normally, a single detection is followed up months or years later with another telescope. But Webb's data quality was so good that NASA and ESA immediately scheduled additional transit observations to confirm the results and expand the wavelength range. By late 2025, those observations will include mid-infrared data from Webb's MIRI instrument, which can detect DMS at longer wavelengths with even greater precision. If that next dataset shows the same pattern, the case will grow much stronger. The importance of this result can't be overstated. For the first time in history, we may have detected a molecule that, on our own planet, is produced exclusively by living things, on a world more than 100 light-years away. That doesn't mean microbes are swimming in alien oceans right now, but it does mean the chemistry of K2-18b is doing something we've never seen before on any other exoplanet. And perhaps the most thrilling part, this is only the beginning. Webb's instruments have observed just a handful of transits for K2-18b so far. Each new pass in front of its star provides more data, sharper spectra, and better constraints on what's really in that atmosphere. The DMS discovery is like a single frame in a much longer movie. What comes next could either rewrite our understanding of planetary chemistry, or give us our first real evidence that life's chemistry isn't unique to Earth. That 99.7% number is what made the K218b story explode. It sounds so definitive, like scientists are saying they're 99.7% sure there's life on that planet. But that's not what the statistic means. In science, especially in astronomy, confidence is a very specific concept. It measures how sure you are that a signal is real, not what caused it. So when researchers say they detected dimethyl sulfide, DMS, with 99.7% confidence, what they mean is that the data they collected fits the signature of DMS so well that there's only a 0.3% chance it's just noise or coincidence. It says nothing by itself about whether life is responsible for making that molecule. To understand this better, think about flipping a coin. If you flip it 10 times and get 7 heads, you might suspect the coin isn't perfectly fair. But you can't be certain. If you flip it 1,000 times and get heads about 700 times, you can calculate the probability that this happened by chance. In astronomy, the same logic applies. Each observation Webb makes is like another coin flip, a data point. The more consistent those observations are with the same molecular fingerprint, the higher the confidence that the molecule is truly there. In technical terms, that 99.7% figure corresponds to what scientists call a 3 sigma detection. Sigma refers to the number of standard deviations a result is away from pure randomness. 1 sigma, 68% confidence, means the result could easily be noise. 2 sigma, 95%, means it's probably real. 3 sigma, 99.7%, means it's very likely real. Most fields of science, including biology and chemistry, consider 3 sigma to be solid evidence. But in astrophysics, where instruments are incredibly sensitive and the data can be affected by countless small variables, the gold standard is 5 sigma, 99.99994% confidence. That's the level required for claiming a new particle in physics, or, in this case, for definitively confirming a molecule's detection. So while 99.7% confidence is impressive, it's not yet enough to declare a discovery beyond doubt. It's the scientific equivalent of saying, this is very likely, but we need more data to be sure. And scientists know how easily subtle errors can creep into this kind of analysis. Even a small mistake in how the instrument's background noise is modelled can make a signal appear stronger than it is. That's why the Webb team use multiple independent processing methods to confirm the DMS result, and why they're planning follow-up observations before making stronger claims. Another key point is that confidence applies only to detection, not interpretation. A 99.7% confidence in detecting DMS doesn't mean there's a 99.7% chance that life exists. It means there's a 99.7% chance that the molecule Webb observed is indeed DMS, or something very similar, given the current models. What made the public so excited was that on Earth, DMS comes almost entirely from living organisms. But those two facts, the detection of DMS and its biological origin, are separate issues. Scientists can be confident about one without yet knowing about the other. This distinction may seem like splitting hairs, but it's crucial in science. The same molecule can have completely different origins depending on its environment. For example, methane, CH4, is produced by both volcanoes and microbes. Oxygen can form naturally when ultraviolet light splits water molecules. Even DMS, though primarily biological on Earth, could theoretically form through unknown photochemical reactions in exotic atmospheres. Until those possibilities are ruled out, the DMS signal remains a biosignature candidate, not proof of life. The process of reaching that level of certainty takes time. The data Webb collected on K2-18b came from just a few transits, only a few hours of total observation. Each additional transit adds new photons, reduces statistical noise, and helps refine the spectrum. The more transits scientists gather, the smaller that uncertainty becomes. If later observations confirm the same DMS features at even higher confidence, say 4 or 5 sigma, then the focus will shift from whether the molecule is real to how it's produced. But even if the number never reaches that threshold, a 3 sigma detection of DMS is still extraordinary. In astronomy, anything above 99% confidence is enough to trigger serious follow-up. It's how every major discovery begins. For example, when the first exoplanet around a Sun-like star was detected in 1995, the initial confidence was barely above 3 sigma. Only after more observations did the evidence become overwhelming. The same will likely happen here: more data, more analysis, and a clearer picture over time. It's also worth understanding that these confidence levels don't come from simple averages. They come from statistical modelling. The Webb team builds computer simulations of what the planet's atmosphere would look like under thousands of different chemical compositions. They then compare each model to the actual observed data, calculating how well each one fits. The confidence level comes from how much better the DMS containing models fit the data compared to all the alternatives. The fact that DMS consistently produced the best fit across multiple methods is what made scientists take it seriously. One thing that caught the team's attention was that removing DMS from the models made the spectra noticeably worse. The data just didn't match as cleanly without it. That's what you want to see if a molecule is really there. It's like trying to play a song on the piano, but skipping one key note. It still sounds similar, but something's off. Add the missing note back, and suddenly everything aligns. DMS was that missing note for K2-18b's spectrum. Still, scientists know how tricky these interpretations can be. Every major telescope has produced results that looked ironclad at first, but later turned out to be false alarms. In 2018, for instance, astronomers thought they'd found phosphine gas on Venus, another potential biosignature, at about 4 sigma confidence. But later analyses showed the signal might have come from noise or calibration errors. That episode made the community even more cautious. No one wants to repeat the same mistake with Webb. So when you see headlines claiming 99.7% chance of life, remember that it's a misunderstanding of what the number actually means. It doesn't quantify belief, it quantifies measurement. It tells us how sure we are that Webb really detected the molecule, not that the molecule was made by living things. But here's the thing, even with that sober perspective, the result is still thrilling. Because what the statistic does mean is that Webb's instruments are now capable of detecting faint, complex molecules, potential biosignatures, at interstellar distances with incredible precision. That's a technological milestone that was unimaginable a decade ago. It's a statement about what we can do, not just what we found. So while 99.7% chance of life makes for a catchy headline, the truth is actually more profound. The number doesn't mean we've discovered aliens. It means we finally built a machine sensitive enough to detect the kind of chemistry life produces, even if that life is hundreds of trillions of kilometers away. And that, all by itself, changes the scope of the question we're asking. Not, is there life out there, but how soon can we find it for sure? To understand why the detection of dimethyl sulfide, DMS, on K2-18b has captured so much attention, it helps to start right here at home. Because on Earth, DMS is an unmistakable signature of life. Every molecule of it floating through our air comes from biology. There are no volcanoes, lightning strikes, or deep-sea vents that make it in measurable amounts. It's a chemical whisper from the oceans, produced by microscopic organisms that most of us never notice, but that quietly shape the entire planet's climate. On Earth, the story of DMS begins with phytoplankton, tiny photosynthetic organisms that drift in the sunlit layers of the sea. These microbes form the foundation of the marine food web and play a huge role in cycling elements like carbon and sulfur. Inside their cells, they make a compound called dimethyl sulfoniopropanate, DMSP. It's essentially a stress buffer. It helps them regulate salinity and temperature changes in seawater. When the plankton die or when something eats them, enzymes break DMSP down into DMS gas, which escapes into the ocean and then diffuses into the atmosphere. Once in the air, DMS doesn't stick around long. Sunlight and oxygen tear it apart within days, transforming it into tiny sulfate particles that act as cloud condensation nuclei. In other words, DMS literally seeds clouds. Those clouds reflect sunlight and cool the planet, creating a feedback loop between marine life and Earth's climate. It's one of the clearest examples we know of life directly, influencing a planet's atmosphere on a global scale. That's why finding DMS, or even something resembling it, on another world is such a big deal. Its presence suggests a system where chemistry is being constantly replenished. not just left to drift toward equilibrium. In lifeless atmospheres, gases tend to settle into predictable, stable ratios determined by temperature and photochemistry. But life disrupts that balance. It continuously injects certain molecules into the air, creating mixtures that shouldn't persist otherwise. DMS is one of those molecules, short-lived, reactive, but always there because something is making more. The quantity of DMS on Earth is small compared with gases like carbon dioxide or nitrogen, yet its impact is enormous. Estimates suggest that marine plankton emit between 20 and 30 million tons of DMS each year, enough to influence global weather patterns. The compound's distinct sulfur smell, the scent of the ocean, of tidal flats and sea spray, is familiar to anyone who has stood near a shoreline. It's the smell of microbial life doing chemistry on a planetary scale. So when astronomers saw Webb's data hinting at DMS in K2-18b's atmosphere, they recognized that pattern immediately. The molecule's infrared absorption features matched what we observe here on Earth. To be sure, the team ran their models with and without DMS, testing whether other gases could mimic its signature. They couldn't. The match was too specific. And because DMS is fragile, easily broken apart by ultraviolet light, the fact that it appears at all means there must be an active source, replacing it continuously. On K2-18b, that source could, in principle, be biological. The planet's hypothesized global ocean offers a natural environment where chemistry could unfold, much like it does on Earth's seafloor or in its upper ocean layers. Even if the ocean there is deeper, saltier, and under immense pressure, the basic recipe for DMS production isn't hard to imagine. On Earth, similar sulfur cycling reactions occur in environments ranging from Antarctic ice to hydrothermal vents. They require only simple microbes, liquid water, and access to carbon and sulfur compounds, all of which could, theoretically, exist on K2-18b. But what makes DMS especially powerful as a biosignature is not just how it's made, it's how distinctive it is. Many potential biomarkers, like methane or oxygen, can also be generated by non-biological processes. Methane can come from volcanoes. Oxygen can form when sunlight breaks apart water molecules. But so far, no one has found a plausible way to produce DMS in significant quantities without life. Laboratory experiments have tried to simulate the conditions of hydrogen-rich atmospheres under extreme heat and pressure, yet none have yielded detectable DMS. That doesn't mean it's impossible, but it does make the biological explanation more attractive. There's also a historical angle. The idea that DMS might serve as a universal biosignature isn't new. It's been discussed in astrobiology papers for more than a decade. Researchers proposed that if life existed in alien oceans rich in sulfur and carbon, it might evolve metabolic pathways similar to Earth's microbes, simply because the chemistry is efficient. Sulfur, after all, is abundant, and forming DMS from organic precursors doesn't require oxygen. That makes it a good candidate for life on planets with hydrogen atmospheres, where oxygen might be scarce or absent. In that sense, DMS could be a universal molecule for life's chemistry, not just an Earth-specific oddity. What's fascinating is how DMS connects biological processes to atmospheric behavior. On Earth, variations in DMS emissions influence cloud cover, which in turn affects how much sunlight the ocean absorbs. If a similar cycle exists on K2-18b, even in a much thicker atmosphere, it could regulate the planet's climate in comparable ways. That kind of self-stabilizing feedback, a biosphere shaping its own environment, would be a hallmark of living worlds. Of course, scientists have to consider every non-biological alternative before making such a claim. Could DMS on K2-18b form through photochemical reactions between methane and sulfur compounds high in the atmosphere? Maybe, but so far models can't reproduce the observed spectral features that way. Could volcanic outgassing release organosulfur molecules? Possibly, but the required concentrations would be enormous, far beyond what geology alone could sustain. For now, biology remains the simplest explanation consistent with what we know. Even so, the team behind the discovery has been careful not to overstate it. The detection of DMS is a clue, not a conclusion. It tells us that something interesting is happening on K2-18b, something that keeps injecting complex molecules into its air. Whether that something is chemical or biological is the next question Webb and future missions will try to answer. What's certain is that this single molecule has forced scientists to rethink where and how they search for life. Before Webb, most exoplanet studies focused on oxygen, ozone, and methane as the classic trio of biosignatures. DMS broadens that horizon. It suggests that the fingerprints of life might come in many forms, some of which we've barely begun to recognize. And perhaps most importantly, it underscores how interconnected biology and atmosphere really are. Here on Earth, you can stand by the ocean, breathe in that faint sulfuric tang, and realize that you're literally smelling the byproduct of microscopic life forms maintaining the planet's balance. Now, 124 light years away, we may be seeing the same chemistry written into the air of another world. If that connection holds true, it means life's chemistry isn't a local accident. It's a universal story, written wherever the conditions are right. The moment DMS appeared in the Webb data, every scientist involved knew what would come next: skepticism. And not in a dismissive way, but in the careful, methodical way that science demands. Because as extraordinary as a potential biosignature sounds, it's also exactly the kind of claim that must be tested, torn apart, and rebuilt before anyone can even whisper the word life. Whenever a molecule linked to biology shows up in an alien atmosphere, the first question isn't, what life form made this? But, could anything else have? On Earth, DMS comes almost exclusively from living organisms, but that's on Earth, an oxygen-rich planet with mild pressures, moderate temperatures, and a nitrogen-dominated atmosphere. K2-18b is a very different world, a mini Neptune wrapped in hydrogen and helium, possibly with a hot, deep ocean beneath. The chemistry there could follow rules that don't exist here, so before calling it a biosignature, scientists have to explore every plausible, non-biological pathway that might produce the same signal. One of the first alternatives considered was photochemistry, the reactions driven by starlight in a planet's atmosphere. The idea is simple. Ultraviolet radiation from K2-18's red dwarf star could hit gases like methane, hydrogen sulfide, or carbon disulfide, breaking them apart and recombining them into new compounds, possibly even DMS or something similar. On paper, that sounds feasible. The atmosphere is already rich in hydrogen, and sulfur compounds are common in planetary chemistry. But when researchers modelled those reactions, the numbers didn't add up. Even under generous assumptions, photochemical processes couldn't produce enough DMS to match what Webb detected. They also tended to generate other gases, like sulfur dioxide or carbonyl sulfide, that Webb didn't see in the data. Another possible explanation was volcanic activity. On rocky planets and moons in our own solar system, volcanism plays a major role in shaping atmospheres. Volcanoes release sulfur-bearing gases like hydrogen sulfide, H2S, and sulfur dioxide, SO2, which can react with carbon compounds to form organosulfur molecules. Maybe K2-18b had massive planet-wide volcanism churning out sulfur gases that later transformed into DMS through high-pressure chemistry. The problem is that K2-18b probably doesn't have a solid surface in the usual sense. Its immense pressure would crush rock into strange phases of ice or mineral, and any volcanic vent would have to push through thousands of kilometers of supercritical water and gas. Even if that somehow happened, most sulfur would be trapped in deeper layers, not escaping into the upper atmosphere where Webb could detect it. Then there's lightning, one of nature's most powerful chemical engines. On gas giants like Jupiter and Saturn, lightning helps create a zoo of complex molecules in their upper atmospheres. Could K2-18b storms be doing something similar, turning methane and sulfur gases into DMS? Again, models suggest not. Lightning can indeed synthesize sulfur compounds, but it tends to destroy DMS faster than it makes it. The result would be trace amounts far below Webb's sensitivity, not a detectable signal. There's also the idea of abiotic surface chemistry, reactions happening at the interface between an ocean and atmosphere. On early Earth, such reactions helped form many prebiotic molecules before life emerged. Perhaps K2-18b's ocean, if it exists, is undergoing similar chemistry, creating DMS-like compounds through reactions between organic molecules and sulfur ions. But there's a catch. These reactions are slow and inefficient without biological catalysts, enzymes that speed them up by orders of magnitude. Without life, the ocean would need far more energy or reactants than seem available to produce DMS at measurable levels. Some researchers have even proposed deep thermochemical synthesis, where extreme pressures and temperatures near the core could fuse simpler molecules into DMS or related organosulfur species. After all, at tens of thousands of atmospheres of pressure, chemistry behaves differently. Molecules that would fall apart on Earth might be stable there, and vice versa. The trouble is, those depths are likely far below the layers Webb can see. Even if DMS somehow formed deep down, getting it to the upper atmosphere would be another challenge entirely. It would have to survive transport through layers hot enough to destroy most organics, and yet we see no trace of the intermediate compounds that such a process would produce. This doesn't mean non-biological processes are impossible, just that none currently fit the data cleanly. Science always keeps the door open for new mechanisms, especially in environments as alien as K2-18b's. The universe is notorious for surprising us. Methane on Mars, for example, once seemed like a possible biosignature. Now we know it can come from purely geological reactions between water, rock, and heat. If something similar happens on K2-18b, scientists will find it. But for now, the known chemistry doesn't explain what Webb saw. Another line of questioning involves instrumental and statistical artifacts. Could the DMS signature be a mirage caused by noise in Webb's sensors, or a coincidence in how light interacts with clouds and aerosols? The team took that possibility seriously. They ran simulations removing the suspected DMS bands entirely, reprocessing the data with different calibration parameters, and comparing the outcome with blank sky observations. The signal persisted. It appeared at the same wavelengths in multiple instruments and in separate transits. That doesn't eliminate every uncertainty, but it makes an instrumental glitch unlikely. There's also the question of spectral confusion, whether another molecule with similar absorption features could masquerade as DMS. Complex hydrocarbons like ethane or propane can sometimes overlap with sulfur compounds in infrared spectra. But again, Webb's wide wavelength coverage gives it an advantage. The instruments detected several distinct DMS bands, not just one, and the overall pattern matched DMS much better than any hydrocarbon tested. In short, scientists have spent months trying to make the DMS signal disappear by explaining it away. So far it hasn't. That's not proof of life, but it's exactly how scientific confidence builds. The more alternative explanations you eliminate, the more the remaining one, no matter how extraordinary, demands attention. Still, even the most optimistic researchers acknowledge that K2-18b's DMS might eventually turn out to be something new in chemistry, rather than biology. That outcome would still be remarkable. Discovering a novel chemical process in an alien atmosphere would deepen our understanding of planetary science and expand the boundaries of what we consider normal. But until that alternative process is demonstrated, the possibility of life remains on the table. This cautious approach reflects how modern astrobiology works. Gone are the days of sensational, life-found announcements based on ambiguous data. Today's scientists know that credibility matters more than hype. Each potential biosignature must pass through a gauntlet of skepticism, replication, and refinement. That's what makes any surviving claim so powerful. The truth is, the DMS detection doesn't tell us exactly what's happening on K2-18b. It simply tells us that something unusual is shaping that planet's atmosphere, something we don't fully understand yet. It might be alien life, it might be exotic chemistry, or it might be a mix of both. Whatever it is, it's a signal worth chasing. And for astronomers, that's the real excitement here. Not the headline, not the hype, but the mystery. Because every time nature gives us a puzzle like this, it forces us to push our understanding of physics and chemistry just a little further. Whether or not life is the answer, K2-18b has already done its job. It's made us ask better questions about how worlds breathe, evolve, and maybe, just maybe, live. Everything we know about K2-18b comes from the faintest flickers of light. Barely perceptible dips in brightness that last only a few hours each time the planet crosses its star. That's the central challenge of modern exoplanet science. We're trying to characterize entire worlds without ever seeing them directly. Webb doesn't take pictures of K2-18b, It measures how starlight interacts with its atmosphere, photon by photon, and from that, scientists try to reconstruct what kind of place it might be. It's like trying to learn the ingredients of a soup by looking at how steam bends the light from a candle. For a planet like K2-18b, every measurement is fragile. Its parent star, a dim red dwarf, is variable. Its brightness can fluctuate because of star spots or magnetic activity. Those changes can mimic or distort the signals astronomers are trying to isolate. Even Webb, as powerful as it is, can't escape the limits of noise and calibration. To extract a planetary spectrum, researchers have to subtract out the star's light, the telescope's thermal background, and the tiny systematic wobbles caused by temperature shifts in Webb's mirrors and instruments. Only after all that can they start to see the subtle molecular fingerprints that define a planet's air. This process, known as spectral retrieval, is as much an art as it is a science. Teams use complex algorithms to fit theoretical spectra to the observed data, adjusting variables like temperature, cloud height, and molecular abundance until the simulated curve matches reality. But there's no single correct solution. Several combinations of gases and temperatures might fit equally well, and deciding which one makes the most physical sense requires both data and judgment. That's one reason astronomers always emphasize uncertainty. For instance, when Webb detected methane, carbon dioxide, and the possible DMS signal, the data didn't reveal exactly how much of each was present or where in the atmosphere they were concentrated. The models suggest DMS exists in trace amounts, less than 1 part per million. But even that estimate depends on assumptions about how light scatters through the clouds. If the atmosphere contains aerosols or haze, they can mute certain spectral features, making a molecule appear less abundant than it really is. Conversely, a clear atmosphere could exaggerate the strength of a signal. So when scientists talk about confidence levels, they're referring not only to whether a molecule is real, but also to how well they understand these complicating factors. Then there's the problem of time. K2-18b orbits its star every 33 days, and Webb can only observe it when the geometry lines up perfectly, when the planet passes directly in front of its star from our perspective. That alignment happens maybe twice a month, and each transit lasts only a few hours. Webb must capture as much light as possible in that short window, and every second counts. Even tiny vibrations or shifts in the telescope's pointing can introduce errors. It takes multiple transits, sometimes dozens, to build up a statistically solid signal. Add to that the immense distance. Light from K2-18b takes 124 years to reach us, meaning every observation is already more than a century old by the time it hits Webb's detectors. If the planet's atmosphere changed recently, say through a major volcanic eruption or a surge in biological activity, we wouldn't see that yet. We're always looking into the past. That delay doesn't make the data useless, but it adds perspective. When we talk about potential life on K2-18b, we're talking about what may have existed there in the early 1900s, not necessarily what's happening right now. The challenges don't stop there. Red dwarfs like K2-18 are notorious for their stellar flares, sudden bursts of high-energy radiation that can fry instruments or overwhelm data with noise. During one of Webb's early K2-18b observations, the star produced a mild flare that briefly spiked the infrared readings. The team had to carefully model and remove that flare's signature from the data before analysing the planet's spectrum. If they hadn't, it could have mimicked false signals or obscured real ones. There's also the issue of planetary geometry. If K2-18b is tidally locked, as models suggest, one hemisphere constantly faces its star, while the other sits in eternal darkness. That means the side we see during transit might not represent the whole planet. The day side could have completely different chemistry from the night side, depending on how heat and wind circulate. Some gases might condense into clouds on the dark side, while others build up on the illuminated half. Webb's current data can't separate those hemispheres. It gives us only an average view along the planet's limb. Future telescopes, like the planned Extremely Large Telescope, EALT, in Chile, or NASA's concept missions such as LUVOIR, may eventually map such differences directly. And even if Webb's data are perfect, interpretation bias remains a risk. Astronomers, being human, know what they hope to find. When the goal is to detect signs of life, there's a fine line between cautious optimism and overfitting the data to match expectations. That's why Webb's exoplanet studies are conducted by multiple independent teams using separate methods. The group that led the DMS discovery shared their raw data openly so others could attempt to replicate their results, a step that builds confidence and helps prevent self-confirmation. Despite these hurdles, Webb's approach represents the best possible method for studying distant planets today. The telescope's instruments are so stable and sensitive that they can detect differences in light intensity smaller than 1 part in 10,000. That precision allows scientists to read the faint imprints of gases that would otherwise be invisible. Each transit builds on the last, sharpening the picture, like adding brushstrokes to a distant landscape that's gradually coming into focus. But even with all that technology, there are limits we can't escape. We can't see weather systems, land masses, or oceans directly. We don't know if K2-18b has continents, or if it's entirely water. We can't yet measure the surface pressure, or detect biological pigments the way we can on Earth. All we can do is read the atmosphere's composition and compare it to what we know from planetary physics and chemistry. In many ways, we're learning to describe a planet by its breath, by the gases it exhales into space. That's what makes studying K2-18b both thrilling and frustrating. It's like having a pen pal across the galaxy who only sends messages in coded chemical patterns. Webb gives us a way to decode those messages, but not yet to see the person or the planet behind them. Every spectral line we record is a clue, but not a photograph. Every molecule is a hint, but not an answer. And yet, those tiny signals are enough to start rewriting our understanding of the cosmos. Even without an image, Webb has already told us that K2-18b has water, methane, carbon dioxide, and perhaps dimethyl sulfide, a mix that's chemically intriguing and physically plausible for a life-friendly world. That's a monumental achievement. The challenge now is patience. More observations are coming, more data will refine the models, and every new transit will peel back another layer of uncertainty. But until the day we can image these worlds directly, we'll be working in the dark, using light itself as our only tool to study places we can't touch, can't see, and can only imagine. And in a way, that's the beauty of it. We're learning to understand planets not by visiting them, but by listening to the faint, rhythmic pulse of their atmospheres, signals that have travelled for over a century to reach us, whispering across the void that there's more out there than empty space. Even with all the caveats, the uncertainties, the alternative explanations, and the cautious language from scientists, the potential detection of DMS on K2-18b remains one of the most important moments in modern astronomy. It doesn't matter that it's not proof of life yet. It matters that for the first time, our instruments are good enough to notice. That's a threshold humanity has been trying to cross for decades. The ability to remotely sense the chemistry of a distant planet in enough detail to say, something interesting is happening here. Before Webb, exoplanet science was mostly about finding planets and estimating their basic traits: size, orbit, mass, and maybe a rough idea of their atmosphere. Hubble and ground-based telescopes could detect broad features like water vapour, but they couldn't distinguish one complex molecule from another. Webb changed that completely. Its infrared sensitivity allows it to read an atmosphere like a barcode, separating subtle variations in absorption that older instruments would have blurred into noise. With K2-18b, it's proven that we can now detect faint, life-linked molecules from over 100 light-years away. That technical leap alone is historic. Humanity has moved from wondering if other planets could host life to actually searching for signs of it with scientific precision. Think about the scale of that achievement. Photons that left a distant star in the early 1900s passed through the thin shell of gas around a planet we'll never visit, travelled across interstellar space for 124 years, and then struck Webb's mirror in 2025. From those photons, literally specks of energy, we can infer not only that the planet exists, but that its air might contain molecules produced by biology. That's not just impressive science, it's one of the most extraordinary uses of light in human history. But beyond the technology, this detection matters because it shifts the conversation about what habitable really means. For most of the last century, the search for life was focused on Earth-like worlds, rocky planets with thin atmospheres, mild temperatures, and liquid water on the surface. K2-18b is none of those things. It's larger, wetter, and wrapped in hydrogen. A world that, until recently, few would have called promising. Yet it's the first to show a credible sign of possible biology. That single fact forces us to widen our imagination. It also represents the payoff of decades of methodical groundwork. The discovery of exoplanets began in 1995 with 51 Pegasi b, a hot gas giant far too extreme for life. Since then, we've catalogued over 5,000 confirmed worlds, most of them too large, too hot, or too cold. Each one taught us something about how planetary systems form and evolve, slowly refining our understanding of where habitable conditions might appear. K2-18b is part of that legacy, a planet chosen not because it looked like Earth, but because it challenged the assumptions that habitable has to mean familiar. And then there's the scientific discipline behind the discovery. What makes this detection different from past false alarms is the rigor of Webb's data and the transparency of its analysis. When scientists thought they'd found phosphine on Venus in 2020, a potential biosignature gas, the initial observation came from a single radio telescope, operating near the edge of its capability. The signal was faint and later proved controversial. By contrast, Webb's K2-18b data came from multiple instruments, repeated observations, and independent processing pipelines. The team went out of their way to release their raw data for others to review, knowing full well that extraordinary claims demand extraordinary scrutiny. That openness is part of what makes this result credible, even if it's still tentative. Even skeptics agree that Webb's detection marks a new level of precision. It shows that we've reached the point where we can detect trace molecules, fractions of a part per million, in atmospheres dozens of light years away. That's an astonishing level of sensitivity, especially when you remember that we're measuring the difference between starlight that passed through a planet's atmosphere and starlight that didn't. It's like detecting the taste of salt in a swimming pool by analysing the colour of the sunlight reflecting off it. But the significance goes deeper than just technical capability. The presence of DMS, even as a possibility, hints that planetary chemistry might be more complex and dynamic than we thought. Until now, most exoplanet atmospheres we've studied were dominated by simple molecules: hydrogen, helium, methane, carbon monoxide. K2-18b shows that heavier, more intricate compounds can exist and persist in those environments. That opens up an entire new class of worlds for study. Planets with enough internal and atmospheric complexity to support rich chemistry, possibly even biology. There's also something quietly profound about the way this discovery redefines first contact. If DMS really does come from life, it won't be intelligent civilizations sending radio messages. It'll be microbes changing their atmosphere molecule by molecule. We wouldn't even need to see them to know they're there. Their existence would be written in the chemistry of their sky. That kind of discovery would be humbling. Proof that life doesn't need to be advanced or aware to be extraordinary. It just needs to exist. And even if it turns out that DMS on K2-18b is abiotic, it still reshapes the field. The discovery shows us the boundaries of what's detectable, pushing scientists to develop more refined models and to search for other, equally subtle signatures. It tells us that we're looking in the right places, using the right tools, and asking the right questions. And perhaps most importantly, it proves that biosignature science isn't science fiction anymore. It's a working discipline, one we can now practice in real time. It's easy to underestimate just how far we've come. In 1990, when Voyager 1 turned its camera back toward Earth to take the pale blue dot image, astronomers could barely detect the presence of other planets at all. 35 years later, we're analysing the air of a planet more than 100 light years away and finding molecules that, here on Earth, mean life. That's a staggering leap in capability in a single human lifetime. For scientists, this moment is both thrilling and sobering. It's thrilling because it proves that our technology is finally powerful enough to tackle the oldest question humanity has ever asked. Are we alone? It's sobering because it reminds us how careful we must be when we think we see an answer. Each signal must be verified, each model refined, each assumption tested. That's what makes the eventual truth, whatever it turns out to be, so meaningful. So yes, even without confirmation of life, this detection is a big deal. It's not just a result, it's a milestone. marking the beginning of a new era in planetary science. We've reached the point where looking for life isn't just a philosophical question or a science fiction trope. It's a practical, measurable pursuit, grounded in data and executed with precision. Whether DMS turns out to be biological or not, K218b will be remembered as the planet where the search for life truly entered the realm of evidence. It's the world that proved we can finally read the chemical fingerprints of another planet's story, and perhaps in time, recognize a familiar signature written in alien air. K2-18b didn't just give scientists a possible hint of life, it gave them a brand new category of worlds to think about. Before Webb's observations, exoplanet researchers tended to divide planets into two main types: terrestrial, rocky like Earth, Mars, or Venus, and gaseous like Jupiter and Neptune. Everything in between, planets with thick atmospheres but smaller than gas giants, was seen as a grey area, a set of bodies that probably weren't habitable because they were thought to have crushing pressures, no solid surfaces, and no clear boundaries between air and liquid. K2-18b changed that perception almost overnight. This planet seems to belong to a class that's now called Haitian worlds, a term coined in 2021 to describe planets with hydrogen-rich atmospheres overlaying potentially global oceans. The name blends hydrogen and ocean, and that combination is key. Hydrogen atmospheres, though thick, are surprisingly transparent in the infrared range, which means they can let light and heat circulate efficiently. Meanwhile, an ocean, especially a deep one, can store and distribute that heat evenly, keeping surface or near-surface conditions relatively stable. Put those two things together, and you get a planet that, even if it's far larger and more pressurized than Earth, could maintain liquid water and moderate temperatures over huge stretches of its surface. For decades, planetary habitability was defined in Earth-centric terms: a thin nitrogen-oxygen atmosphere, moderate pressure, and surface water. But if Haitian worlds can truly host life, the implications are enormous. Hydrogen is the most common element in the universe. That means these planets could be far more abundant than Earth-like ones. Instead of being rare oases, habitable environments might be scattered throughout the galaxy. Billions of them, hidden under layers of gas that our old instruments simply couldn't read. The concept of Haitian habitability is based on both observation and physics. In a hydrogen-dominated atmosphere, the greenhouse effect works differently than on Earth. Hydrogen itself is a poor greenhouse gas, but when it's mixed with water vapour and methane, it traps heat efficiently without letting the planet overheat. This balance creates a broad sweet spot for temperature, one much wider than Earth's classical habitable zone. Even worlds orbiting relatively dim red dwarfs like K2-18b can stay warm enough for liquid water. In fact, some models suggest that Haitian planets could remain habitable far beyond the range where Earth-type planets would freeze solid. There's also a biological advantage to hydrogen atmospheres. They make chemistry easier. Hydrogen is highly reactive and can help form complex organic molecules from simple precursors like carbon dioxide and nitrogen. On early Earth, before oxygen took over our air, hydrogen-rich conditions may have been crucial for forming amino acids and other building blocks of life. A Haitian planet could recreate those primordial conditions on a global scale, offering a continuous factory for organic chemistry. Scientists have already identified dozens of exoplanets that might fit this description: super-Earths and mini-Neptunes with radii between 2 and 3 times that of Earth, orbiting in the temperate zones of small stars. K2-18b is simply the first to show atmospheric data strong enough to support the idea. But it's likely just one of many. If even a small fraction of these planets have oceans and stable climates, the number of potentially life-friendly worlds in our galaxy could jump by orders of magnitude. The potential diversity among Haitian worlds is staggering. Some may have clear skies and shallow seas. Others might be wrapped in thick clouds or have dark, stormy atmospheres where sunlight barely penetrates. Some could have chemical cycles dominated by carbon and hydrogen, while others might involve nitrogen or sulfur. Life on such worlds, if it exists, might look nothing like life here, perhaps relying on methane instead of water as a solvent, or using completely alien biochemical pathways. But the fundamental requirement remains the same: an energy source, a liquid medium, and a stable environment where molecules can assemble and evolve. K2-18b appears to tick several of those boxes. Its temperature, based on Webb's data, falls in the range where water could exist as a liquid beneath the atmosphere. Its detected gases, methane, carbon dioxide, and possibly DMS, point to active chemistry. And its size and mass suggest a dense envelope of hydrogen overlaying a water-rich interior. All of these clues fit perfectly within the Hysian model proposed just a few years earlier. If this interpretation holds, K2-18b may be the prototype for a whole new family of habitable planets. That's why the discovery has rippled through the exoplanet community. It tells scientists where to look next. Instead of focusing only on Earth-sized rocky planets, they can now target slightly larger, puffier ones around small stars, objects that were previously dismissed as too extreme. These worlds are easier to detect and analyze because their large atmospheres create stronger spectral signals during transits. In other words, Hysian worlds are both more common and more measurable, a dream combination for observers. It's also helping refine our understanding of how planetary systems form. Traditional models assumed that once a planet reached a certain size, it would become a mini Neptune, with no hope for life. But K2-18b and its cousins suggest that under the right conditions, say a moderate hydrogen envelope over a deep ocean, a planet can exist in a long-term, stable balance. Instead of being suffocated by its atmosphere, it could use it as insulation, keeping the interior warm and liquid for billions of years. That's a radically new way to think about habitability. There are even subcategories within the Hysian family. Cold Hysian planets might orbit farther from their stars, relying on internal heat to keep their oceans from freezing. Hot Hysian worlds could lie closer in, with thick clouds reflecting starlight to prevent runaway warming. Dark Hysian planets could be tidally locked, with one perpetual night side where life might thrive under faint starlight or geothermal glow. Each of these variations expands the range of possible life-supporting environments far beyond the narrow band we once considered viable. If life truly does prefer chemistry over comfort, if it just needs a stable liquid environment and access to energy, then Hysian worlds might outnumber Earth-like ones by a huge margin. They could be the galaxy's true life factories, and common, diverse, and persistent. That realization is quietly transforming astrobiology. In practical terms, it's also changing mission planning. Space agencies are now prioritizing Hysian candidates for future observation. Webb's successors, missions like LUVOIR, HabEx, and the Origin Space Telescope, are being designed with the sensitivity to detect a broader range of gases across these hydrogen-rich atmospheres. Researchers are already compiling shortlists of targets, planets orbiting nearby red dwarfs with radii around 2 to 3 Earths, where transits are frequent and easy to observe. Every one of them could be another K2-18b waiting to surprise us. The theoretical implications reach even further. If Hysian worlds can host life, that means life may not be a rare fluke of perfect conditions. It may be a natural outcome of planetary evolution. The chemistry that makes Earth's oceans fertile might be playing out across countless other systems. It might even suggest that the first life in the universe didn't appear on rocky planets at all, but in the deep, high-pressure oceans of hydrogen-wrapped worlds orbiting dim red stars. For now, K2-18b stands as the best-known example, but it's likely only the beginning. Webb's observations hint that we've been looking for life in the wrong places, guided by the bias of our own biology. As new data come in, those biases will fade, replaced by a more universal view of habitability, one defined not by resemblance to Earth, but by the fundamental rules of chemistry and energy. That's the bigger picture this discovery opens up. Whether or not DMS on K2-18b turns out to be biological, it's already changed how scientists think about where life might exist. The universe may be full of worlds we once ignored, thick-aired, ocean-covered, glowing softly under red suns, each one quietly cycling molecules, waiting for us to notice. K2-18b simply reminded us to look. The James Webb Space Telescope's discovery on K2-18b was never meant to be the end of the story. It was designed to be the beginning. Every intriguing molecule Webb detects sets up the next round of questions. Is it really there? How much is there? And what else might be hiding in that atmosphere? The upcoming Webb observation cycles are built around answering exactly those questions, with a level of precision that would have been unimaginable just a few years ago. In the wake of the DMS and DMDS findings, NASA and the European Space Agency immediately scheduled follow-up transit observations of K2-18b. The goal is to capture additional data at longer wavelengths using Webb's mid-infrared instrument, MIRI, which can see deeper into the planet's atmosphere and detect molecules that NIRS-PEC and NIR-ISS might miss. MIRI operates from about 5 to 28 microns, where complex organic compounds, sulfur species, and other potential biosignatures leave their most distinct spectral fingerprints. If DMS truly exists in the atmosphere, MIRI should pick up independent confirmation lines that don't overlap with those found by Webb's near-infrared instruments. That's crucial because multiple detections across different wavelengths are how scientists move from possible signal to confirmed presence. It's like identifying a song not just by its rhythm, but also by its melody and lyrics. Seeing DMS at several unrelated wavelengths would drastically reduce the chance that the signal is a coincidence or an artifact of data processing. The next step is to map out the chemical environment surrounding the DMS. Webb will focus on other gases that could help explain the planet's chemistry, particularly ammonia, NH3, hydrogen sulfide, H2S, and carbon monoxide, CO. These molecules play important roles in sulfur and carbon cycles. If K2-18b's atmosphere contains DMS but very little ammonia or carbon monoxide, it would strengthen the case for an active biological process, because on a purely chemical world, those gases tend to appear together. If, on the other hand, all of them show up in balanced amounts, that would point toward non-biological chemistry at work. Either outcome would be valuable. Both would reveal more about how Hycean atmospheres behave. Webb's follow-up campaign will also aim to determine cloud structure and temperature profiles. One of the biggest uncertainties in the current models is whether the planet's clouds are made of water, hydrocarbons, or something more exotic like ammonium hydrosulfide. Clouds influence how starlight filters through the atmosphere, affecting every spectral feature. By comparing data from different wavelengths, some that pass easily through clouds and others that are heavily scattered, scientists can estimate the altitude and composition of those cloud layers. If they find gaps or clear windows in the atmosphere, that could help narrow down where the detected molecules are coming from. Another key target for Webb's next observations is temporal stability. Are these molecules constant from one transit to the next, or do their concentrations fluctuate? On Earth, seasonal changes in biological activity alter atmospheric chemistry in measurable ways. Think of the annual rise and fall of CO2 tied to plant growth. If K2-18b shows variations in DMS or methane over time, it could hint at dynamic processes, whether biological or geological. Repeated transits will test for that, providing a sort of primitive weather record for an alien planet. Beyond Webb, other observatories are lining up to get involved. The Hubble Space Telescope will continue to provide complementary ultraviolet and visible light data, which can constrain how radiation from the host star interacts with the atmosphere. The James Clerk Maxwell Telescope in Hawaii and ALMA in Chile, both operating in the sub-millimeter range, may attempt to detect thermal emission from the planet or search for related sulfur compounds at different altitudes. Together, these observations could create a multi-layered picture of K2-18b's atmospheric chemistry from top to bottom. Meanwhile, teams of chemists and planetary scientists on Earth are working to model non-biological production pathways for DMS. They're recreating K2-18b's hydrogen-rich environment in high-pressure laboratory chambers, exposing gas mixtures to ultraviolet light to see whether DMS or DMDS can form spontaneously. So far, early tests haven't yielded results matching the observed ratios, but experiments are just beginning. These lab studies will help determine whether life is truly the simplest explanation, or whether some exotic, abiotic chemistry can mimic its signal. The Webb team will also refine its retrieval algorithms, the software used to interpret spectra. Current models assume a relatively uniform atmosphere, but future ones will simulate more realistic conditions, gradients in temperature, uneven cloud coverage, and the possibility of vertical mixing between layers. The more sophisticated those models become, the better scientists can distinguish real molecules from optical illusions caused by overlapping spectral features. Over the next year, as more transits are observed, Webb's data will likely double or triple in volume. That will reduce statistical noise and push confidence levels higher. A 4 sigma or 5 sigma confirmation of DMS would be a turning point. It would all but eliminate the chance of a false detection. At that point, the conversation would shift from, did we really see it, to what's producing it? If Webb confirms the DMS lines, scientists will look for correlated patterns among other molecules. For instance, if DMS increases while methane decreases, it could mean photochemical breakdown is occurring. If both remain steady, it might suggest a stable biological or chemical source, maintaining equilibrium. Webb's instruments are sensitive enough to detect those relative changes, even if the absolute quantities remain uncertain. These ongoing observations will also prepare the ground for the next generation of telescopes. Missions like the Nancy Grace Roman Space Telescope, launching later this decade, will specialize in direct imaging of exoplanets, literally blocking the light of the parent star to see the planet's reflected glow. Roman won't have Webb's spectral resolution, but it could help confirm which planets are good candidates for detailed follow-up. Further out, projects like LU, VOIR, and HABEX, if approved, would combine direct imaging and high-precision spectroscopy, finally allowing scientists to take spectra of Earth-sized worlds instead of just sub-Neptunes. In the meantime, Webb will keep refining its focus on K2-18b, accumulating more data with each transit. Every additional observation narrows the margin of error and clarifies the picture of what's happening inside that distant atmosphere. By mid-2026, scientists expect to have a full suite of spectra, spanning from near to mid-infrared, offering the most detailed chemical map of an exoplanet ever created. No matter what those data show, whether DMS turns out to be a true biosignature or a quirk of alien chemistry, the implications will be profound. If confirmed, it would be the first verified detection of a biologically linked molecule beyond the solar system. If disproven, it will still give us the most complete understanding yet of how Hycean atmospheres work. Either way, it moves us forward. And perhaps most importantly, Webb's continuing investigation of K2-18b demonstrates that the search for life is no longer just speculative philosophy. It's an active, ongoing scientific process. Each new observation refines our instruments, our methods, and our imagination. Whether the next round of data strengthens or weakens the case for life, it will teach us how to look better, measure better, and think bigger about what a living planet can be. K2-18b might have grabbed all the headlines, but it's far from the only world under Webb's microscope. The telescope's success in detecting complex chemistry there has effectively opened the floodgates. Now, astronomers are pointing Webb, and every other available instrument, toward a growing list of planets that could offer similar surprises. These suspect worlds are the next big step in finding out whether K2-18b is an outlier or just one of many worlds quietly breathing complex gases into space. At the top of that list is a system that's already famous, TRAPPIST-1. Discovered in 2017, this compact star system, only 39 light-years away, has 7 Earth-sized planets orbiting a single ultra-cool red dwarf. 3 of them, TRAPPIST-1e, F, and G, lie within the star's habitable zone, where temperatures might allow liquid water. They were once considered our best shot at finding Earth 2.0. But when Webb began studying the system, early results complicated the picture. So far, the telescope has found that TRAPPIST-1b and C, the 2 innermost planets, likely lost their atmospheres long ago, stripped away by intense stellar radiation. That doesn't rule out habitability farther out, though. TRAPPIST-1e and F are still promising candidates, and Webb will soon target them with longer, deeper observations. Scientists hope to see whether their atmospheres contain carbon dioxide, water vapour, or other life-related molecules. If any of those signatures appear, the TRAPPIST system could become the next big K2-18 moment. Another intriguing world is LHS 1140b, about 48 light-years away, in the constellation Cetus. It's slightly larger than Earth and orbits a quiet red dwarf star that emits far fewer flares than K2-18's host. That stability makes it easier to study. What's especially exciting about LHS 1140b is that its density suggests it might be a water world a planet covered in a deep ocean, tens or even hundreds of kilometers thick. Hubble and ground-based telescopes have already detected hints of a thin atmosphere, and Webb's early observations in 2024 hinted at the possible presence of water vapor. If confirmed, LHS 1140b could become a second Hycean-type example, reinforcing the idea that K218b isn't unique. Then there's Kepler 138d, about 218 light-years away. Discovered in 2014, it was long thought to be a rocky super-Earth. But new modelling in 2022 revealed that it's probably composed mostly of water, possibly up to 50% by volume. It, too, orbits a red dwarf, and though it's warmer than K2-18b, its atmospheric pressure could keep that water in a liquid or supercritical state. Webb's instruments are scheduled to examine Kepler 138d in an upcoming observation window to look for methane, CO2, and, if we're lucky, similar organosulfur compounds like DMS. There are also GJ1214b and GJ486b, two of the most studied mini-Neptunes to date. GJ1214b, located just 48 light-years away, was one of the first planets where astronomers detected a thick atmosphere using Hubble. The problem was, Hubble couldn't tell what the atmosphere was made of. Its data were muddied by high-altitude haze. Webb changed that. In 2023, it produced a stunning thermal emission spectrum that showed the planet's air likely contains both water vapor and methane. That combination doesn't mean life, but it suggests a rich, active chemistry. In many ways, GJ1214b is a warmer cousin to K2-18b, a world that could show how Hycean-like planets evolve closer to their stars. GJ486b is the opposite case, a hot rocky planet only slightly larger than Earth. It's far too close to its star for liquid water, but Webb's observations found faint signs of water vapor high above its surface. The big debate is whether that vapor belongs to the planet or the star, whether it's an atmospheric remnant or simply a feature of the star's corona. Either way, the detection demonstrates how sensitive Webb's instruments have become. If it can spot trace water on a blazing, airless world like GJ486b, it can certainly tease out more subtle molecules on cooler, ocean-bearing planets. Another target that has scientists buzzing is TOI 700d, discovered by NASA's TESS mission in 2020. It's an Earth-sized planet, orbiting in the habitable zone of a quiet M-dwarf about 100 light-years away. It's smaller and cooler than K2-18b, which makes its atmosphere harder to detect, but it represents the next logical step, an attempt to bridge the gap between large, Hycean-like planets and truly Earth-like ones. Webb will likely attempt its first transit spectroscopy of TOI 700d in the next few years, searching for water vapor, methane, or perhaps even ozone. And then there's Wolf 1069b, one of the most Earth-like exoplanets discovered so far. It orbits a calm red dwarf just 31 light-years away and sits comfortably within the habitable zone. It doesn't transit its star, which makes spectroscopy difficult, but upcoming instruments like the ELT, Extremely Large Telescope, in Chile and the 30-meter telescope in Hawaii may be able to detect its atmosphere using a different technique called high-dispersion spectroscopy. If they can confirm the presence of carbon dioxide or water vapor, Wolf 1069b could become a key comparison point for Webb's findings on K2-18b. Beyond these, astronomers are beginning to catalogue dozens of other candidates. K29b, HD3167c, LP791-18d, and GJ9827d, each of them small, relatively nearby and orbiting dim red stars that make their transits easier to observe. Some may have atmospheres thick enough to retain water vapor. Others could be completely stripped bare. Webb's role will be to sort them out, molecule by molecule, until we understand which ones might truly host life-friendly conditions. What's exciting about this next phase is that the technology finally allows for comparisons across worlds. For the first time, astronomers can look at multiple exoplanets with similar temperatures, sizes, and stellar types and start to see patterns. Do methane and water often appear together? Are certain molecules more common around quiet stars versus active ones? Is DMS unique to K2-18b, or will it pop up elsewhere? These are questions that couldn't even be asked 5 years ago. Now they're central to the field. This comparative approach will also help scientists avoid jumping to conclusions too early. If another Hycean planet shows DMS or a similar sulfur compound, it would suggest a broader chemical phenomenon, possibly biological, possibly not, but at least not a one-off anomaly. On the other hand, if Webb finds no DMS anywhere else, then K218b becomes even more special, perhaps hinting that it's home to something unique. In the bigger picture, all these investigations are part of a deliberate roadmap for the search for life beyond Earth. The idea isn't to find one magic planet and declare victory, it's to build a statistical understanding of how common life-related chemistry might be. Just as Kepler showed us that planets are everywhere, Webb is beginning to show that complex atmospheres are too. The next generation of instruments will take it further, moving from how many have interesting molecules to how many are alive. So while K2-18b currently stands in the spotlight, it's really just the first chapter of a much larger story. Dozens of other worlds are waiting in Webb's queue, each with its own secrets, its own chemistry, its own potential to surprise us. If even one of them echoes what we've seen on K2-18b, the question of whether life exists beyond Earth will shift from speculation to expectation. And if several do, then we'll know that biology isn't the exception in the universe, it's the rule. The discovery of dimethyl sulfide on K2-18b has brought scientists closer than ever to identifying a credible biosignature beyond Earth, but there's still a huge gap between possible sign of life and confirmed life. In astrobiology, that line isn't crossed easily, and it shouldn't be. To claim that we've found life on another planet, scientists need more than one molecule and more than one observation. They need a converging body of evidence, multiple independent signals that all point to the same explanation, and that can't be accounted for by non-biological chemistry. So what would it actually take to confirm life on a distant planet like K2-18b? The first requirement is repeatability. Webb's data has to hold up under further scrutiny. That means observing several more transits, ideally in different conditions and with different instruments, to show that the DMS signal doesn't disappear or shift with new data. A one-time detection, no matter how strong, can always be a fluke. But a signal that appears consistently, at the same wavelengths with the same intensity, across multiple observation campaigns becomes extremely hard to dismiss. If Webb's MIRI instrument detects DMS in the mid-infrared range, confirming what NIR specs saw in the near-infrared, that alone would push the detection toward a much higher confidence level. The second requirement is context. What other molecules exist alongside DMS, and in what ratios? Life doesn't act in isolation. On Earth, biological activity leaves a chemical fingerprint that's recognizable by its internal balance. Oxygen paired with methane, for instance, or carbon dioxide coexisting with DMS in unstable proportions that wouldn't persist without constant renewal. That kind of chemical disequilibrium, a mix of gases that shouldn't naturally coexist, is one of the most powerful indicators of life. If Webb's future data show that DMS, methane, and carbon dioxide are present together in steady but incompatible concentrations, that would suggest something is actively maintaining that balance, just as photosynthesis and microbial metabolism do here. The third requirement is elimination of abiotic explanations. This is the painstaking process of ruling out every possible non-biological source. It involves high-pressure chemistry simulations, computer models of photochemical reactions, and deep atmospheric dynamics modeling to see whether any known physics could reproduce the observed data. If none can, the biological hypothesis becomes not only plausible, but necessary. This step often takes years. It's exactly how scientists eventually confirmed that oxygen in Earth's atmosphere is biogenic. No geological process can produce it in such abundance without life. The same standard would apply to DMS or any other candidate molecule. The fourth and most definitive line of evidence would be correlated biosignatures, different molecules linked through known biological pathways. If, for example, Webb or future telescopes detect both dimethyl sulfide and methyl mercaptan, or see dimethyl sulfide fluctuating in tandem with methane or carbon dioxide over time, that could point toward biological cycling. Life tends to leave patterns, not isolated signals. On Earth, Marine microbes that emit DMS also influence methane oxidation and sulfur dioxide levels. These interrelated processes create chemical rhythms that chemistry alone can't easily mimic. Detecting such coordinated variations in an alien atmosphere would be the equivalent of hearing a choir instead of a single voice. It's what would move scientists from possible to probable. Long-term monitoring would add another layer of confirmation. If the DMS concentration changed seasonally or periodically, perhaps in response to the planet's orbital cycle or star brightness, that would suggest active replenishment, potentially biological. Abiotic sources tend to be steady. Living systems are dynamic. A planet that breathes even subtly is one that deserves attention. The fifth piece of evidence scientists would look for is consistency with environmental conditions. If K2-18b truly has a hydrogen-rich atmosphere over a deep ocean, any biosignature must make sense in that context. For example, DMS production on Earth depends on the availability of sulfur, carbon, and energy from sunlight or chemical gradients. On K2-18b, the same elements exist, but sunlight is weaker and filtered through a thick atmosphere. If the observed DMS levels fit what a plausible microbial ecosystem could produce under those conditions, that strengthens the case for biology. If the quantities are far higher or lower than expected, the explanation might lie elsewhere. Eventually, direct imaging will become the ultimate test. Right now, Webb can only analyse starlight that passes through the planet's atmosphere. But future missions like LUVOIR and HABEX are designed to take actual pictures of exoplanets and their reflected light. That will allow scientists to measure surface colours, brightness changes, and even polarisation patterns that reveal clouds, oceans, or vegetation analogues. If a Hycean world ever shows a combination of biosignature gases and surface features consistent with an active climate system, the evidence for life would be overwhelming. One of the most compelling future approaches will involve detecting time-resolved spectra, watching how a planet's light changes as it rotates. On Earth, if an alien telescope were to observe us, they'd see the spectrum shift as continents, oceans, and vegetation move in and out of view. Chlorophyll, for instance, leaves a strong red edge reflection feature that oscillates daily. Detecting something similar, any recurring spectral change that implies surface diversity or biological pigments would add yet another layer of proof. Of course, confirmation will never rely on a single instrument. In the coming decade, Webb will be joined by a fleet of telescopes that can observe the same planets from different angles and wavelengths. The European Southern Observatory's Extremely Large Telescope, ELT, will use adaptive optics and high-dispersion spectroscopy to isolate planetary light from its star, making it possible to cross-verify Webb's results. The Nancy Grace Roman Space Telescope will survey thousands of nearby stars for new candidates, while missions like Ariel, ESA, will specialise in comparing atmospheres across dozens of worlds. Together, they'll create a network of independent confirmations, the scientific version of triangulation. But the final threshold for claiming life goes beyond detection and confirmation. It's about confidence beyond reasonable doubt. When every known abiotic pathway is exhausted, when multiple biosignature gases are observed in the right proportions, when seasonal or cyclical variations are evident, and when all instruments agree, scientists will finally be able to say that the simplest, most consistent explanation is biology. That moment would carry the same weight as the discovery of DNA or the detection of gravitational waves, a shift not just in data, but in humanity's place in the universe. If that day comes, and it could, in our lifetime, it won't arrive with fireworks or a press conference about aliens. It will come quietly, as a graph, a paper, a set of overlapping lines on a spectrum that collectively say, this can only be life. And the beauty of that truth is that it won't rest on belief or speculation. It will rest on light, measured with precision, decoded by physics and verified by the consensus of science. For now, we're still a few crucial steps away from that level of certainty. But K2-18b has shown that we finally have the tools, the patience, and the understanding to get there. Confirmation may take years, but the path is clear. And when we do cross that line, from detection to declaration, it won't just confirm that life exists elsewhere. It will confirm that the universe is, in its own way, alive. Every time a new sign of life headline flashes across the internet, scientists flinch a little. Not because they don't want it to be true, but because they know how easy it is to get it wrong. Space history is littered with moments when data looked convincing, the world got excited, and the story eventually collapsed under the weight of reanalysis. That's why, even in the face of a result as intriguing as dimethyl sulfide on K2-18b, the scientific community is deliberately cautious. Avoiding false positives isn't just a matter of reputation, it's built into the very structure of how planetary science operates. The first safeguard is redundancy. Every major telescope observation, especially one involving potential biosignatures, must be repeated multiple times, and ideally with multiple instruments. Webb itself is designed with overlapping detectors, NIRISS, NIRSPEC and MIRI, all capable of viewing similar wavelength ranges, but using different technologies. When all three see the same feature at the same wavelength, the odds of an instrumental error drop dramatically. It's the same principle as using 3 cameras to photograph the same scene. If one shows a smudge, you check whether it appears in the others before assuming it's real. The second safeguard is independent analysis. After the initial discovery team publishes their results, other scientists, often competitors, download the raw data and run their own pipelines. They might use slightly different calibration methods, statistical models, or assumptions about the planet's atmosphere. If the new analyses reach the same conclusion, confidence grows. If they diverge, the debate begins. In the case of K2-18b, multiple research groups have already begun their own analyses of Webb's data, testing whether the DMS signature holds up under different processing conditions. The goal isn't to disprove one another, it's to pressure test the result until only the strongest explanations survive. Another key practice is model comparison. Every retrieval of an exoplanet atmosphere starts with assumptions about temperature, cloud coverage, and gas mixtures. But those assumptions can bias the outcome. To counter this, scientists run dozens or even hundreds of models with varying parameters, asking a simple question: which ones fit the data best? If DMS only appears under a narrow set of assumptions, that's a warning flag. If it appears consistently across many independent models, that's a sign the signal is genuine. This process of cross-model validation is what turned the initial detection of DMS from a curiosity into a result worth talking about. Then there's the peer review process itself. Before any claim like this sees the light of day, the paper must be reviewed by anonymous experts who comb through the methodology, statistics, and reasoning. Reviewers often ask the authors to reanalyze the data using different techniques or to include simulations of potential false positives. Some studies take months to clear review because of the back-and-forth revisions. It's slow but deliberate. Peer review isn't a formality. It's the scientific equivalent of a stress test. Even after publication, scientists rely on post-publication scrutiny. Planetary detections are never accepted instantly. They earn credibility through time and replication. When phosphine was reported on Venus in 2020, other teams immediately reanalyzed the radio data and couldn't reproduce the signal. Within a year, the claim had largely unraveled. That experience reshaped the community's standards for biosignature claims. Now, extraordinary detections are expected to include full data transparency, independent verification, and, ideally, multiple lines of evidence. The Webb teams learned from that lesson. They released their K2-18b datasets publicly, inviting scrutiny from day one. Another protective layer is theoretical skepticism. For every potential biosignature, there are groups dedicated to studying false positives, natural processes that might mimic life's chemistry. These planetary chemists work hand in hand with observers, constantly testing whether exotic but non-biological pathways could create the same signals. The process might sound adversarial, but it's what keeps the field honest. In fact, many of the leading experts on DMS as a biosignature were also the first to publish papers, outlining how it could, theoretically, form without biology. The tension between excitement and skepticism drives the science forward. Scientists also use Bayesian statistics to quantify uncertainty. Instead of just saying a detection is 99.7% confident, they calculate how much prior evidence supports the interpretation. For instance, we already know DMS is rare in non-biological chemistry. that prior knowledge influences the probability that the detection represents life versus noise. By folding those priors into the models, researchers can update their level of confidence as new data arrives, a process known as Bayesian updating. It's how they keep their conclusions flexible rather than absolute. And there's a cultural safeguard too: professional restraint. Within astronomy, it's understood that any extraordinary claim must survive a long gauntlet of skepticism before it's considered real. Scientists don't want another Mars microfossil moment, when a 1996 NASA announcement about life in a Martian meteorite dominated headlines, only to crumble under later analysis. Since then, NASA and ESA have adopted strict language guidelines for how they present potentially groundbreaking findings. Instead of saying evidence of life, they use terms like biosignature candidate, tentative detection, or statistical indication. It may sound cautious, even anticlimactic, but it preserves scientific integrity. The collaborative nature of modern astronomy also helps prevent groupthink. Webb's data are stored in open archives, accessible to thousands of researchers worldwide. That means any graduate student or independent scientist can challenge the findings of even the most prestigious team. It's a level of transparency that wasn't possible in earlier eras of space exploration. And it ensures that errors can't hide behind closed doors. Sometimes the safeguards come from unexpected directions. For instance, artificial intelligence and machine learning now play a growing role in analysing spectra. While these tools can process enormous datasets far faster than humans, they can also introduce bias if trained on incomplete or Earth-centric examples. That's why researchers validate AI-generated detections using traditional physics-based methods. No signal is accepted purely on a machine's word. Ultimately, avoiding false positives comes down to a simple principle: extraordinary claims require extraordinary evidence. Scientists treat the detection of extraterrestrial life not as a discovery to rush toward, but as a hypothesis to eliminate every alternative from. In a sense, the goal is to make the biological explanation the last one standing. Only when all other options have been exhausted, instrumental, chemical, statistical, can they responsibly say, this must be life. For now, that cautious discipline is exactly why the K2-18b result is so compelling. The team didn't rush to proclaim discovery. They presented a candidate and invited the world to check their work. Every skeptical question strengthens the case if the signal survives. And if it doesn't, the process still succeeds because it shows the system works. That science can be self-correcting, honest, and patient enough to wait for proof. In many ways, that's what separates scientific excitement from wishful thinking. The public may crave certainty, but scientists know that truth, especially cosmic truth, takes time. The real story of K2-18b isn't just that Webb might have detected life. It's that we now have a community and a framework strong enough to test that idea without being fooled by our own hopes. For all the excitement surrounding K2-18b, what's most remarkable is that this story isn't ending. It's just starting to unfold. The James Webb Space Telescope has given us a glimpse of what's possible, but the next decade will determine whether that faint chemical whisper in another world's atmosphere becomes the first confirmed proof of life beyond Earth. The immediate priority is confirmation. Webb will continue observing K2-18b through 2026, using every instrument available to recheck the DMS signal and search for supporting gases. The data pipeline will evolve, noise models will tighten, and each new transit will sharpen the planet's spectral fingerprint. By then, scientists expect to know whether DMS was a false alarm, an exotic chemical artifact, or the first sign of biology. Beyond Webb, the next wave of telescopes is already preparing to take over. The Nancy Grace Roman Space Telescope, set to launch near the end of the decade, will perform large-scale infrared surveys, finding thousands of potential Hycean worlds for Webb and its successors to study in detail. The aerial mission from the European Space Agency will specialise in comparing exoplanet atmospheres across hundreds of targets, a kind of cosmic sensors of chemistry. If DMS or similar molecules show up elsewhere, Ariel will find them. Meanwhile, on the ground, a new generation of observatories will come online. The extremely large telescope, ELT, in Chile, with a mirror nearly 40 meters across, will be able to separate starlight from planetary light directly, a capability Webb doesn't have. Its high-resolution spectrographs will reveal the fine structure of alien atmospheres, potentially detecting oxygen, water, and carbon-bearing molecules on smaller, more Earth-like worlds. Paired with Webb's infrared data, the ELT could build the first multidimensional view of an exoplanet's climate and chemistry. Farther ahead lies the next great leap: direct imaging. Concepts like LUV-OIR, HabEx, and Origin Space Telescope are already on NASA's drawing boards. These missions would use massive segmented mirrors and star shading devices to block out the glare of host stars, allowing us to see exoplanets as individual points of light. Once that happens, scientists will no longer rely solely on transits. They'll analyse reflected light from a planet's own dayside, mapping continents, oceans, and weather patterns. The same techniques that spotted DMS in a spectrum could, in a generation, reveal chlorophyll-like pigments or the glint of sunlight off alien seas. Alongside these instruments, computational modelling will keep evolving. Simulations of atmospheric chemistry, once limited by Earth-based assumptions, will incorporate the strange physics of Hycean worlds, higher pressures, thicker gases, and weaker sunlight. Machine learning systems trained on thousands of known spectra will learn to identify subtle correlations humans might miss. Every new observation will refine the models, which in turn will tell astronomers where to look next. The coming years will also bring policy and collaboration changes. The search for life has outgrown any single agency or nation. Webb's data are already analysed by teams across 6 continents, and future missions will require shared investment on a global scale. ESA, NASA, and private foundations are drafting cooperative frameworks to share observation time, algorithms, and laboratory results. If and when a biosignature is confirmed, that discovery will belong to everyone, a product of collective curiosity rather than national competition. And while telescopes aim outward, research here on Earth will mirror that effort. Laboratory teams will continue testing how complex molecules behave in hydrogen atmospheres, trying to replicate what Webb saw on K2-18b. Biochemists are exploring life-in-a-bottle experiments, recreating exoplanet conditions to see what kinds of metabolic systems could emerge. Those studies won't just inform astrobiology, they'll teach us how flexible life's chemistry can be, and perhaps even inspire new forms of biotechnology. But beyond instruments, funding, and models, the road ahead is also personal. For the scientists who've spent their careers staring at faint dots of light, K2-18b represents validation, proof that their tools are finally powerful enough to chase the oldest question with real precision. For students entering the field now, it's a beginning, not a conclusion. The first confirmed biosignature may not come from Webb. It may come from someone who's still in high school today, studying these discoveries and imagining the next generation of telescopes. Whatever the outcome, the K2-18b story has already shifted the trajectory of space science. Even if DMS turns out to be chemistry, not biology, Webb has demonstrated that we can detect biology if it's there. That realization changes everything. The universe is no longer a silent expanse of distant lights. It's a set of worlds we can now read in molecular detail. So the path forward is clear. We'll keep observing, keep testing, keep refining, until one day, maybe not long from now, the data align beyond all doubt. When that day comes, when a spectrum shows the unmistakable signs of a living planet, it won't just answer a scientific question. It will rewrite our story as a species. For now, we're closer than ever. Webb's light has shown us the first hint. The next generation will bring the proof.